So this is lecture number 11. So yesterday we were talking about the stability analysis, and we said that we talked about certain schemes numerically being sometimes some schemes are stable unconditionally, whereas some schemes, in fact we looked at, we talked about the center time center space scheme, Richardson scheme for the parabolic equation, which is unconditionally unstable. So the stability analysis is quite important to help us figure out whether a scheme is stable or not, or if it is stable, under what conditions is it stable. So for that we need a starting point, and the starting point is the update formula for error, and that is what we wrote yesterday. So we'll start from there. So this is the error update formula for the forward time center space scheme for the parabolic equation that we've been talking about. Okay, so this update formula allows us to evaluate the accumulation of the round off errors. Remember, it's the accumulation we're talking about. We're not talking about generation here, because what's important here is to figure out whether the old errors which were generated earlier in the previous iterations, whether they grow with time or they decay with time, and that's a property of the algorithm. That's what we have written here. Okay. So that's what we want to figure out. So for this we will be using something called von Neumann stability or von Neumann error analysis. So that's what we will discuss in this lecture number 11. Now this error that we are talking about is a function of both x and t in this case, right? Because the problem is a function of x and t, theta is a function of x and t, so error will also be a function of x and t. So if I was to let's say plot the error at any time, let's say t equal to t1, so what I would see is that it will vary something like this. Okay. Yes. For what? Sorry. Linear. Linear what? Linear equation. So we are talking about linear equation. So we are talking about a particular equation called parabolic. But why do you think that the error will work only for linear equations?
Because we are taking difference of absolute value and numerical value. That's why we are getting error.
Right. So error is defined that way. It's a difference between the exact solution to the difference equation and the solution that we are getting from our computer. So that has nothing to do with whether the equation is being linear or non-linear. Right, because see, error will always be there, and that error is defined as the difference between your actual difference equation solution and your solution of the computer from the computer. Right? But this discussion that we are having is for linear equation only. Anyways, this concept is valid for non-linear equations as well, and that's the whole idea. See, our equations, actual equations that we want to work with, Navier-Stokes equations, the momentum equation, they are non-linear, and doing a non-linear error analysis is complicated, quite complicated. So what we do is we do an error analysis for linear equations like the one that we're dealing with, and then we will try to extrapolate these ideas to the non-linear equations. Okay. So the blue one is what the error will typically look like. Okay, and the boundaries I've kept the error 0 because let's say we have Dirichlet boundary conditions. If you know the boundary conditions exactly, then the error will be 0. But in the interior of the domain, the error will be non-zero. It could be either higher or lower than the actual solution. That is irrelevant. What matters is how far the solution is from the exact solution to the difference equation. That's D that we call. Okay. Now this is some sort of a function, and we know that from the idea of Fourier series, if a periodic function is there, then you can write it as a sum of infinite number of sines and cosines which have different frequencies. Okay. So I can write this as so let's look at it for this particular situation where t is equal to t. So let's look at it for a given time. So then epsilon is only a function of x in this case. So if you look at the complex Fourier series that I have written here, this one. So what this tells us is that I am writing this epsilon at a given time t1 as a superposition of different waves. So I could draw it so there is a wave with a very low wave number k. So k is the wave number here. Okay, and ak is the amplitude. Of the corresponding wave. Wave number is an equivalent of angular frequency in space. Okay, so we'll have this is half a wave, but you could extend it. So this is a wave with the lowest wave number, okay. And then I can have another wave which is got higher wave number than this. That's another wave, and then so on, and then you can have very high wave numbers. For instance, something like this. Okay, and so on. So this blue one is very high k, and the red one is in fact the lowest k that is possible in this case. Just like low k. So I write assuming periodic function, that's because since you are writing this epsilon as a sum of different waves, now these waves are periodic, they don't end within the domain. If you write let's say sine kt, sine kx, then that's a periodic function, right? So that's defined for all values of x. So we assume that this error function, the blue one that I have drawn above, is periodic. So whatever we have here, it sort of starts repeating. But that's okay, because our domain is only between x and L. So it doesn't really matter whether the function is periodic or not, as long as it is the values are correct within x equal to 0 and x equal to L. Okay. It's giving extra information if it predicts things outside, but that there is nothing outside. So that's just because of the idea of Fourier series, that you're getting information everywhere, but it should be correct within the domain. Okay. Now strictly Fourier series, if you expand this epsilon as a sum of different, so what e to the power j kx, from the Euler's formula it becomes cos kx plus j times sin kx. So it's got a real part and an imaginary part. So what we really want to look at is the real part, not the imaginary part. But it's much easier to deal with the whole complex epsilon rather than deal with the real part every time. So we deal with the whole complex epsilon. Okay. Right. So the idea of Fourier series is that I can write any function, because error is some arbitrary function of x. I am not going to detail of when you can write a Fourier series or not, but let's assume that you can write it. The function is nice enough to do that. So in that case, what we are doing is we are writing it as a sum of different waves. So a red wave, a green wave, and a blue wave, and there's three. You can have infinite number of them, and the amplitudes of different waves are different. So if your error actually was behaving like the blue wave in the below figure here, so what happens is that the amplitude of blue wave would be some constant and the other amplitudes would be 0, right? That's one way to write this blue wave, is to simply keep its amplitude some finite value and the others are 0. But in reality, if you have an arbitrary function like the error function that I have drawn above, the amplitudes will all be finite. Some of them will be small, some will be large, depending on the nature of the behavior of the function. So in this error function, you can actually see some sort of a wave number here, and then some small fluctuations that you might see here, some fluctuations here, they also have some frequency. It's like the Fourier decomposition that you do. So the idea of Fourier series is that all waves contribute, some contribute more than the other. So the ones that contribute more will have higher amplitudes as compared to the ones that contribute less. Okay. Now this error, the figure that I drew above, is for a given time. As time changes, error will change, error everywhere will change. So my plot of error with x for a different time, let's say t2, will look different, right? So what I do is, to write a function of x, we are getting contribution from all frequencies, from all wave numbers, but the amplitudes will change with time. So to fit a different function at a different time, what we have to do is we have to simply change the amplitudes corresponding to those waves, because all the infinite waves are contributing. So it's only the amplitude that will change. So if you tweak the amplitude for each wave, then you will get a different function. Okay. So that's the reason this amplitude ak for the wave with wave number k is a function of time. Is that clear? Now k in this case, because the domain is not from 0 to 2 pi, it's from 0 to L. So this is written as m pi upon L, where m goes from 0 on. So if m is 0, you get a constant. So there could always be a constant term in a Fourier series. Everything could be shifted above the epsilon equal to 0. In this case, that's not the case. In this case, the constant term will not be there. Then m equal to 1 is pi by L. So that's the red wave I have drawn here, right? Because the domain length is L. So one full wave will be of size 2L in this case. So pi by L is the largest wave, and as m increases, you will see that the wave number or the frequency increases. Now, if you have, since we are talking about discretized domain, so let's say you discretize the domain to have a total of capital N number of intervals. So what will be the largest value of m possible there? Because see, we are talking about a discretized domain here. So I mean, let's say the wave could only pass through the nodal points. That's n, right? So if you have a domain which had a certain number of points, so if you draw it like this, I mean anything beyond that we cannot resolve. So that's sort of the largest frequency that we can capture. So if your signal had, if your error had a stronger fluctuation, so let's say this is your discretized domain and you have these nodal points, and your error in reality, okay, I am not talking about the solution to discrete equation, let's talk about the actual PDE. In that case, the solution was fluctuating like this. So it has a lot of fluctuation, but all you are capturing is the value here, here, here and here. So all the fluctuations between those two nodal points are lost, right? And this is the idea of sampling. Have we learned about sampling? People in this class? Sampling frequency and so on, yes, right? So you can, the best frequency you can capture is dependent on the number of sampling points you have. So you cannot have more information than that, even though the actual signal could be making a lot of fluctuations with a higher frequency than what you can capture, but that is lost. Okay, similar is the idea here. So m can max be n here, nothing beyond that. I mean, you can have more larger m, but then those contributions would be 0 because you cannot capture that in this situation. Another idea is that the different k modes that we are talking about, the different wave number modes, they are independent. That's another idea of Fourier series, that these are independent, they don't reinforce each other. So if you have a wave number which has a certain amplitude, then that is sort of independent from the other wave number. You can think of it as these different frequencies as different as basis for your space. Linear algebra, you have, for example, in a 3-dimensional space you have bases x, y and z. So I hat, j hat and k hat are independent directions. So if you have a certain component in I hat direction, that does not change the components in j and k direction. Similarly, these modes are independent. So you can take an inner product. I am not going there, but you can take inner product of functions also, and then you will see that these different frequencies are independent. The inner product becomes 0. Typically in courses, in the heat transfer course, you would learn about that when you try to find the analytical solution in 2D heat conduction problem using separation of, I mean, have you done PDEs, partial differential equations? Is that a part of mathematics course? No. Okay, so I mean you if not there, then probably some other course. Typically heat conduction course will solve the two-dimension heat conduction problem analytically using separation of variables, and there you get this idea of the independence of the orthogonality of functions. So if the functions are orthogonal, that means that they are independent. That's one way to say. Another way to say that, so different k modes are independent, so they don't feed each other. The other thing is that I mean from this what we interpret is that overall, remember the idea is that the error should not grow with time, it should typically decay with time or decay with iterations. Now since error is a linear combination of different waves, it suffices to say that since all the waves are independent, if none of the waves grows with time, then I am good. Or I can say if all the waves decay with time, then things are good. Right. So this is the main idea now. Now we will convert this statement to a mathematical statement and then start working with the working on the mathematics here. Okay. I'll just repeat the idea that we are writing epsilon as a linear combination. If you look at the epsilon function here, what we are doing is we are writing as a sum of different harmonics. E to the power j k x is simply think of it as cos k x if you take the real part. So different k values will give us different waves, different cos functions, and then a k's are the corresponding amplitudes. So it's a linear combination of different cos waves. So what I am saying here is that since all the waves are independent, so if all of them decay with time, then the scheme is going to be stable. And even if one of them starts growing with time, think of it, I mean you are writing a wave a function error as sum of different waves. The amplitudes could be different to start with, but what happens is one of those, the amplitudes start increasing. So what you would see is that although the others are small, but let's say the green one here starts growing, the overall sum has a contribution from the green one, and that amplitude is becoming large and large. So what you would see is that after a few iterations that will dominate and it will become out of bounds, or it will become unbounded. Okay. So what we do is we use the error update formula to show the boundedness of epsilon, and for an arbitrary k, because we want to show the boundedness for all k values. So what we do is we keep k arbitrary. I don't choose a value of k. I just keep it as a variable k, and as a result my boundedness should not be a function of the value of k. It should be true for all values of k or for any arbitrary k. Okay. So that's the whole idea of von Neumann stability analysis. By the way, von Neumann was a Hungarian scientist, and he has contributed in almost all fields of science, including mathematics, physics, economics, computing, stats, and so on. You will hear the name in different fields. He was a polymath. So he's contributed a lot to engineering as well. So let's use these ideas to perform von Neumann stability analysis for the forward time center space scheme that we've been talking about. So we'll use the error update formula for that scheme. Now before that, how do we show that error is not increasing, or for a given wave k the error is not increasing with time? So for that, the idea is amplitude, right? Because otherwise it's just a cos wave. So if the amplitude at time t plus 1 is not higher than the amplitude at time t, then that means the error is either neutral, it's not it's either not growing or it's decaying. So the condition will be that a at n plus 1 about a at n should be less than equal to 1. So I'll tell you what this a n plus 1 means. So error function, now we're talking not in terms of this Fourier series, we'll talk only in terms of one wave, just one of those waves. So the summation is gone. So I've just chosen one arbitrary wave with a wave number k, and the corresponding amplitude is a. So I'm not using the subscript k in this case for a, because it's known that it's for some arbitrary k. So in our update formula that we have here, we have a superscript for time and a subscript index for x. Is that for attendance? Okay. Now the index for time, since it's only the amplitude that's a function of time, so we put that index on a, and remember x for a homogeneous element size is delta x times the index I. So if we take the amplitude of error, we simply get the, if we take the mod of that, we simply get the amplitude. The amplitude of e to the power of j k x is 1, right. So what we are trying to say is that the ratio of epsilon n plus 1 I and epsilon n I should be, or the mod of that should be less than 1. Then things are good. And this actually is called the amplification factor. Now typically amplitudes are, amplitude is taken as positive, but when you do calculations, what you see is that sometimes you get a negative. So you have to be strictly saying that the mod of g which is the magnitude of the amplitude at n plus 1 time divided by the magnitude amplitude at nth time, that has to be less than equal to 1 for stability. So, if you think of a wave, you start with some amplitude, and if the amplitude decays with time, that basically means that the error is decreasing with time, and that is happening for all k values, because we have taken an arbitrary k. We are imposing this condition on an arbitrary k value. If your g is actually greater than 1, and if g is equal to 1, then we call it a neutrally stable or just a neutral scheme. Errors are not growing. Any questions till this stage?
सर जी जो है वो आपने टाइम का फंक्शन बनाया
A, yes.
पर वो स्पेस का फंक्शन है
No, so okay, let's reiterate the idea. So, if you look at the error at a given time, it's this blue wave that I have drawn on the top. It's a function of space, right? Now, we are writing this function as a sum of infinite number of cos functions with different frequencies. Now, when the time changes, the function will change. So, the way to change the function is we are changing the amplitudes corresponding to different frequencies, right. So, the different frequencies are for space, and when you change the amplitude at a later time, you can control the shape of the function. That is the reason what we have done is we have taken a only as a function of time and the oscillating part as a function of space. Is that clear? Any other questions? It's a very beautiful idea, this stability that we are doing here. Right, so let us substitute this into our error update formula now. Right. So, now I will do some algebra. So, I will divide everything by a n and also divide everything by e to the power of j k delta x I. Now, e to the power of j k delta x is cos k delta x plus j sin k delta x. So, if you add these two terms, we get a real number. So, I can take the 2 outside. Right. Now, gamma here is alpha delta t by delta x squared. We already defined that earlier. It is called the numerical Fourier number. Now, cos well, there's an identity cos 2 theta is 1 minus 2 sin square theta. Is that correct? So, using this identity, we can write cos k delta x minus 1 as minus 2 sin square k delta x by 2. So, I will take the minus outside, and then we get a 4 here. And this is our amplification factor. So, the idea is to basically get an expression for the amplification factor, that is a n plus 1 upon a n, using the update formula for error. And once you have that, we simply have to apply the condition that mod of g has to be less than 1 for stability. So, this gives us two conditions, or this says that your g has to be between minus 1 and 1. In that case, mod of g will be less than 1, right. In some cases, you will see less than equal to 1, because equal to 1 will also not grow, but it is always good to keep it less than 1 strictly to ensure that it decays with time. So, let us look at this function. Yes. Right, it's a very good question. I mean, amplitudes typically are positive, but if you look at this function, what you see is that it's 1 minus something. So, it can actually go below 0, right. So, amplitudes we take them as positive, but ultimately it could be either positive or negative. So, we have to ensure that the magnitude is less than 1. Okay. So, g has to be between minus 1 and 1 here. Now, if you look at this function 1 minus 4 gamma, gamma is a positive number. It is alpha delta t by delta x squared. Diffusivity alpha is always positive. Negative diffusion is physically not possible. So, alpha that is given to you in the problem will always be positive. Okay. Delta t and delta x definitely by definition, the way we have defined are positive interval sizes. So, gamma is positive. Now, sine square of anything has to be positive or non-zero, greater than equal to 0. So, what we see is that 1 minus 4 gamma sine squared k delta x by 2 is going to be a quantity always less than 1. So, 1 minus a positive quantity, that is less than 1. So, this actually gives us two conditions. One is to check if g is less than 1, and the other one is to say g is greater than minus 1. So, this is true always. nothing to check here. So G, now the only condition we have to check is G greater than -1. Or I mean, you have to find the condition under which G is greater than -1, because we are doing a stability analysis. It could be a conditionally stable scheme. So if I mean G less than 1 does not give us anything, because it's always true, which is good. I mean, for unconditionally stable scheme, you will get both conditions as always true. So that's unconditionally, but in this case actually it's a conditionally stable scheme. So when you apply G greater than -1, that gives us 1 minus 4 gamma sine square k delta x by 2 is greater than -1. So we'll again do some work on inequality here. So I can divide both sides by 2. So this is the stability condition we get. Gamma times sine squared k delta x by 2 has to be less than half. Now remember, this has to be true for all k values. Only then my scheme is stable. That's what we said. We'll start with an arbitrary k and ensure that the condition is met for this arbitrary k. Now you're saying gamma times something has to be less than half. So the worst case scenario is when this something is equal to 1, because it's a sine squared can at max be 1. See, taking smaller values will give you conditions which may be true for some k values. If I say gamma times a small number is less than half, it could be true. But if your sine square k delta x is equal to 1, that's the worst case scenario. So if that condition is true, then it's true for all k values. Right, so this ensures stability for all k waves. So gamma was defined as alpha times delta t by delta x squared, that has to be less than half. In fact, if you look at the assignment, I have asked you in one of the problems to analyze the solution as you change gamma. So as you change gamma, you would see that if your gamma, initially I think I have given you as 0.1 to start with, and you will see that you get a good solution which matches with the analytical solution that's available for that situation. But as you go beyond 0.5, you see that the solution starts to blow up, and if it's close to 0.5, then you get numbers which are large if you have finite number of iterations, but they are absurd. But if you go for slightly larger, let's say 0.7, 0.8 values of gamma, you would see that the solution actually blows up to not a number. So that is something that you can play around with in your program and ensure and check that this condition actually makes sense. So that's the beauty of this analysis, that this helps us figure out under what situations is the numerical solution stable. It has nothing to do with the actual problem. The problem still has a solution. I mean, the differential equation has nothing to do with the delta t or delta x, right? That's for our computation analysis that we have broken that into a grid. But for this forward time center space or the explicit scheme, we see that it only works numerically for gamma less than half. Now, what is the meaning of gamma being less than half? Now, gamma is alpha delta t by delta x squared. Now, alpha is based on your physics. I can't play around with that. If you are solving a given situation, alpha is diffusivity, which is based on physics. But delta t and delta x are in our control. So, what that means is for a given delta x, there is a corresponding maximum delta t that you can have. Let me write that down. So, for a given delta x, there is a corresponding maximum delta t, because if you go beyond that delta t, your gamma will become greater than half. So, what is the implication of this condition? Now, let us say I want to increase the accuracy of the problem by increasing in space. So, I increase the value, I decrease the value of delta x. So, if I decrease delta x, I will have to decrease my delta t as well, given that I was working at the edge. Let us say earlier my gamma was 0.49. Now, if I decrease my delta x, my gamma will increase above 0.5, so I have to decrease my delta t as well. So, that means if I have to reach a certain time, I have to increase the number of steps I have to move, and because of this, sometimes what happens is the delta t becomes so small that the number of steps you have to take to reach that time where you want the actual solution becomes prohibitively large, and that takes such a large computation time. You have to take 1,000,000 time steps. So, that computationally becomes expensive. The explicit scheme, which computationally was much easy to implement, actually becomes computationally expensive because of this stability issue. And it is a very major issue in computational sciences, that because of the stability condition, you sometimes your delta t becomes sometimes very, very small. And that is where the backward time center space schemes starts to become interesting. Okay. So, if your delta x, so in CFD what we do is we start with a very coarse mesh. You have implemented a method, you want to make sure that you want to get some idea of the trend of the solution. So, you start with a very large delta x. So, explicit methods will work, because large delta x means that you can work with large delta t's as well. But when you start to make it finer and finer, and you for more higher accuracy in space, you have to start decreasing delta t. So, that is where backward time center space or implicit schemes will tend to shine. So, it is a homework for you to show that the backward time center space scheme is unconditionally stable. So, please using these ideas, try it yourself. This will also reinforce the ideas we have learned today. Yes, question. Yes, because alpha is always positive.
So, ये backward time center space के लिए.
Yes, that has nothing to do with the scheme. Alpha is diffusivity based on physics, and delta t and delta x by definition positive. So, gamma is positive. Yes. So, you think of, so the question is why is G mod G always less than 1 for stability? Is that the question? Is always true? Okay. So, in this case what we see is, look at the function G. G is 1 minus something, and that something is positive. So, if you subtract a positive number from 1, you get a number which is less than 1. Any other questions? Right. Okay. So, attendance, can I have that?